mathematicians. This is kind of the third video in the series, and in this video we're going to practice simplifying radicals. As a reminder, in the last video we learned that a radical is fully simplified when there's no perfect square under the radical, when there are no fractions under the radical, and when there are no radicals in the denominator. Please pause me, and in your math journal or on a whiteboard, go ahead and simplify each of these three radicals. All right, pause me. I'll see you soon. Welcome back. Here are the simplified versions of each of these. If they're correct, all three, bye, see ya, on to the next thing, ready to do some more practice. If not, I'm going to walk through each one, so you can just move forward in the video until you get to the expression or expressions, it might be all three of them, that we'll do together. For this first one, the main thing I'm looking for is, are there any perfect square factors under the radical? Since I don't know right off the top of my head for 147, I'm going to make a little factor tree just to start thinking about what the factors are. I know it's not divisible by 2, it's not an even number, but I do know it's divisible by 3 because the digits add up to 12, and 12 is divisible by 3. And when I did the math, this is 3 and 49. So I see there I have a square number, a perfect square. So this is the same as the square root of 49 times 3. And using one of those properties now, we can distribute that radical to both of our factors. It's the same as the square root of 49 times the square root of 3, which is equal to 7 times the square root of 3. Sometimes we write this, we put the dot there for multiplication, but this is equivalent to just saying 7 root 3 or 7 square root of 3. When there's no operation there, just like 3x, it means multiplication is there. Take a moment and visualize what this means. If I have a square with an area of 147, I can partition it into 49 little squares, each with an area of 3. And then if I'm thinking of the side length of the square, there'll be 7 squares down that side, each with a side length of the square root of 3. So think about that visual. Let's go to the next one. Here, this is really just like doing two separate little problems. I need to simplify my numerator and simplify the denominator. 24 is the same as 4 times 6, and I know I can separate those out into two radicals. Square root of 4 times the square root of 6. My denominator, I have 36 times x to the 6. Again, I can separate those out into two radicals. Square root of 36 times the square root of x to the 6th. I'm going to go ahead and take my square roots that I know of. Oh, excuse me. I made myself just a little bit too big. Square root of 4 is 2. 2 times the square root of 6. And then 6. Let's talk now about how do you take the square root of a variable raised to a power. When I look at x to the 6th, is there a way to write x to the 6th using the exact same power? And there is. I'm going to take this up and make this a little side problem. I can think of x to the 6th. It's the same as x to the 3rd times x to the 3rd. When I multiply powers at the same base, I add the exponent. So I can always take a power and turn it into multiplication using that pattern in the opposite direction. Whenever I see something being multiplied by this itself and I want to take the square root, I know the square root of x cubed times x cubed is simply x cubed. If that feels fuzzy to you, keep thinking about it, pause the video, maybe ask a classmate, ask me, and we can talk about it some more. In fact, in general, you might think, how do we know what types of variables raised to powers can you take the square root of? Last step is always, I look, can I simplify my numbers? They both share the common factor of 2. 2 divided by 2 is 1. 6 divided by 2 is 3. So my final simplified version is the square root of 6 over 3x cubed. All right, let's do the grand finale, the last one. This one, before I do anything, I'm going to start here. No fractions under the radical. So I can distribute that radical to both the numerator and the denominator, equal to the square root of 5 over the square root of 18 times x to the 4th. Nothing more I can do with the numerator. My denominator, 18, is the same as 9 times 2, and I know 9 is that perfect square. So I'm going to write this as the square root of 9 times the square root of 2 times the square root of x to the 4th. Square root of 9 is 3, and the square root of x to the 4th. X to the 4th is the same as x squared times x squared. If I add 2 plus 2, I get 4. So the square root of x squared times x squared is x squared. I've got square root of 5 over 3 times x squared times the square root of 2. My last step now is I can't have a radical in the denominator. I've got to rationalize my denominator, and to do that, I'm going to multiply the numerator and the denominator by the square root of 2. In my numerator, I now have the square root of 5 times the square root of 2. In my denominator, I have 3 times x squared times the square root of 2 times the square root of 2. Right. Square root of 5 times the square root of 2 is the same as the square root of 5 times 2, or the square root of 10. My denominator, square root of 2 times the square root of 2, is just 2. And then 2 times 3 will give me 6. So the denominator is 6x squared. And I'm fully simplified. Mathematicians, I hope this was helpful for you. It's now time to do some more practice, ask questions, ask your classmates, ask me, and I'll see you soon. Bye-bye.